The question for this afternoon was also to talk about, the brilliance of biology, particularly in terms of hydration or the rebuilding of soil hydrologies. And this is really critical, isn't it? Because, as we said, it's these hydrological extremes. And everybody, engineers, everybody can see this because we work through that in a thing called we call hydrographs. Hydro water graph. And all these show is basically what happens to the flow of water over time when we get a rainfall event. So just say we get a 2 inches of 50 millimeter rainfall event. And this is what we're experiencing in this current La Nina, but it's what we experience all the time, even in the drought. And if we've got a degraded soil, as we have over large parts of the landscape, then we get a very clear physical signal on our hydrograph. We'll have a 50 millimeter rainfall event, and of course what we end up with a flood peak that will very rapidly go up very high. It's more or less concreted catchments, water running off those catchments. And of course what we have is a flood. And of course the flood erodes, and a flood basically costs. Massive costs in terms of the damage it does, but also even more costs in the physical infrastructure. When you think of the amount of concrete sunk infrastructure we have to put into culverts and roads and stormwater management that we of course pay for our taxes. Okay, and so basically these become very, very major limitations. But what happens, we get this flood peak, but then very quickly, of course, it floods off. And so by definition, when we've got a hydrograph like this, we've designed in the next step, which is of course the drought. Because the water that in a sense flooded off isn't available. It's gone, caused a lot of damage, but it's now down the creek or in the ocean, but it's lost. And so now we have a drought, and of course the drought erodes in a different way, and it also costs enormously. And so this is in a sense what kills. Okay, so there's water that's life, water gives life, but water also kills, right? It's the thing that does really the damage. And what's happening, we're going to be in a world where, yes, we're getting warming, increased climate change, more evaporation from the oceans, more hydrological extremes, so more floods, erosion costs, death, more droughts, erosion costs, more deaths. You see, and so this is something that's really going to impact, and we in agriculture are going to impact it, but also all of societies. And the issue, what we need, in a sense, to avoid that, of course, are buffers. Okay, so how do we actually buffer these extremes? How do we get resilience? How do we survive those extremes? And in a sense, this is what soil gives us. Because here was a soil, and just say this was a degraded soil, just say at 0.5% carbon. Okay? Because we've oxidized the carbon from the soil largely through our industrial agriculture, which is then obviously oxidizing that carbon back to CO2. But if we bring that same soil back up to 3% carbon, so now we've lifted it to 3% carbon, and we see, as we saw this morning in the soil samples, we've got better structure, better aggregation, rooting to deeper depth. Then with the same rainfall event, we'll get a completely different hydrograph. Okay, so we'll get the same storm event, but it'll come up and it'll form the same volume under graph. I mean, I don't know if I've drawn that exactly right, but you've got the same volume of water, but instead of having a flood peak, this is buffered it out. Now we have basically runoff. Yes, we're going to lose some of this water and runoff, but most of the water is going into our sponge. Okay, into our soil carbon sponge and in soil reservoirs. And we're now in a completely different world. Because instead of being lost, we can put this water in our, in a sense, reserve account in our soils. And now that water is not causing all this damage, but this water is now available in a sense as our drought security. Because it's that water that gives us a longevity of green growth. Fundamental concept, right? Longevity of green growth. So important because we at the moment as farmers are trying to say, can we grow plants faster, bigger, quicker? Okay, can we get a bigger plant growing in the 6 weeks or whatever? Well, that's not important. Because if we can grow plants for longer, 365 days of the year, we've got productivity. Okay, so it's not how fast plants grow, but it's for how long they can grow. When we had basically the flood peak, we had growth, bring it back to this axis, we might have had growth for what, 10 days. So we get a 50 millimetre event, and yes, there's some soil, water soaked into the soil, we've got growth for 10 days. But if we have a sponge and in-soil reservoirs, then we've got a growth periodicity, and that might be 200 days. Now that's a 20-fold increase in productivity. 2,000% productivity dividend. Now unheard of. You know, when I was in CSIRO and when scientists would get a 30% growth response, we'd get a clean white lab coat, a clipboard and queue up for the Nobel Prize. But the point is that 2,000% was undreamt of. But in a sense, that's what nature can give us. And not just nature, that's what rebuilding the soil carbon sponge, rebuilding our in-soil reservoirs, and rebuilding resilient biosystems with longevity of green growth can give us. So in a sense, the brilliance of biology, as we heard this morning, is about building soil carbon, building roots, building structures, but the dividends come in things like these hydrographs, right? And that's really then the very, very valuable take-home for farmers. How do we build buffering, resilience, survivability in our farming systems through building soil carbon? Now, soil politics is all about soil carbon, and can we get some money from soil carbon accounting? We've been involved with that for 20 years, and basically there's been so many policy changes, like whether we will ever get it, I don't know. But that's not the point. The point is it's farmers building buffers, resilience, survivability that counts. So, and it's all available through rebuilding soil carbon. And of course we can do this very simply, naturally, and again we looked at this morning from some of David's sort of thing. Okay, remember he started off with parent material. Here's a rock. A rock is basically a whole lot of mineral particles that obviously fuse together. And of course, if we put water on a rock, we know what happens to it. It runs off, doesn't it? And if we need to get access to nutrients in a rock, just say here's a phosphorus molecule, then basically we've got buckley's because it's all locked up, occluded, unavailable, because it can't be accessed. And in a sense, that's where we were 420 million years ago. The world had evolved life in the oceans. There was teeming life in the oceans, but basically the earth, the land, was dry, hard, desertified rock. But of course, nutrients were leaching from that rock into the oceans, and of course those nutrients were limiting growth of life in the oceans, so there was a competitive advantage of basically growing from the oceans onto the land to solubilize nutrients. And that's the process of pedogenesis, of soil formation, and the guys that are involved with that were, in a sense, our friends the fungi. We talked about the fungi this morning, these hyphae, thin mycelial threads, membrane threads that grow from the estuarine edges onto this rock to help solubilize nutrients. And of course what they did is they basically then took this rock and started breaking it up and solubilizing and leaving behind organic detritus, which are basically the carcasses of the fungal membranes and the hyphal, and leaving that and creating, in a sense, what we simply call the soil carbon sponge. Okay, and so it's the same mineral soil physically. All we've done is we've basically put some organic detritus. No, in this case, 1 to 2% carbon, and we've drawn it as little bed springs to give you the picture of the sponge. But that's really all that soil formation is about. But then you get profound changes, because once I've taken from a solid rock to this, we've fundamentally changed it. First of all, we've made it a lot lighter, and we had that in the balance this morning, because this rock is 2.6 to 3.5 grams per cc. You know, it's above density, the weight per volume. But a healthy soil is basically 1.2 grams per cc. So we can see straight away, well, all we've done is we've added nothing. We've added void, air, nothing. It's half the weight, half of it is just air, void, nothing. Okay, so we build healthy soil by making these sponges, but then only a small fraction. We make a healthy soil by putting nothing into the soil. So don't pay too much for nothing.
Sorry, Walter. Instead of paying farmers for their carbon, can we just pay them for the nothing that they're making?
Yeah, but then how do we sell them nothing? See, that's the thing. How do we put a price on nothing, right? Okay, but the whole point is, in terms of the buffering, this is what you're doing. Now, of course, it's very elementary, isn't it? Because what happens when we put a drop of water on this guy? Obviously, we get infiltration, we got retention, and as we said, longevity of green. And this is so important, because this is what's going to make farming survivability into the future. You know, as climate exchange and stresses intensify, can you build more resilient, buffered farming systems? Can you extend longevity of grain through this hydrology? So, brilliance of biology giving you this hydrology. Now, I haven't got another colour, but we will see. The same thing happens here. We were hunting this phosphoricine. So now we've got that phosphoricine, whereas before it was unavailable, now it is basically available, isn't it? Our fungal hyphae, our organic acids have access to it, so it's now fully available. 90% of the bio-fertility of soil isn't how much nutrients there are. It's not how many of these phosphoricines there are. It's their availability, how fast they can, or how easily they can be accessed, made available through this microbial process that David showed us were critical in taking up in exchange for the sugars from exudates, how much was available, and then also, of course, being available, how efficiently and rapidly it was able to be cycled. For example, in Australia, I was working on rainforests on Fraser Island, Cooloola, with CSO soils. The world's most productive terrestrial ecosystem, effectively on silicon dioxide, cut glass. No, very, very little, up to 1 billion nutrients. But the rainforest was there, so resilient, so productive, because these biofertility cycles were so fast that it was able to sustain those really healthy systems. So again, for us, in terms of agriculture, we've got buffering, and then we've got biofertility. Can we generate biofertility through these sort of processes? Okay, so basically this is in a sense what we're doing from what David explained, building the biology of soils, but recreating the hydrology, the water retention, infiltration, availability, longevity, the biofertility, the rootability of these soils, and through that its resilience and bioproductivity. Critically important.